So pretty quickly, we went through 4 different types of statistical tests, right? We went through linear regression, we went through one-way ANOVA, we went through two-way ANOVA, and we went through t-tests. And again, to stress, right? I'm not expecting you to do this maths. I'm just expecting you to kind of understand what's going on. And what we saw was that the linear regression, the one-way and the two-way ANOVA, all involve calculating F values, then seeing what the probability of getting an F value this large would be if there was no relationship between our data. If our data was all sampled from the same population, and if that was very unlikely to get an F value that large, then we said there was a significant effect. But the t-test was kind of different, right? I mean, it had elements of the same thing. We calculated this t-statistic, and then we said, what is the likelihood of getting a t-value that large if there was no difference between the groups? But it was not the same equation. All of the other ones were, as I say there, explained variation over unexplained variation. But this t-test was like the difference between the groups divided by something to do with the unexplained variation. If you look at it, it's actually pretty similar. But it wasn't the same. And why was that? In fact, one might even think that a one-way ANOVA and a t-test are kind of like they're like brothers or cousins or something, because in a one-way ANOVA you have 3 groups and you want to know if they're kind of different, sort of. It's if there is some if the variation explained by those 3 groups is greater than or is significant relative to the total variation. But really, fundamentally, when we think about it, it's, are these 3 groups different? Well, the t-test is, are these 2 groups different? Okay, so why is it so different? Well, here's a question for you. Is it actually so different? Okay, what happens if you do a one-way ANOVA on 2 groups? We can do it, right? We can make it happen. Okay, so first let's do a t-test. Let's get some data. This is some data I generated vaguely because I was bored, right? Which is my reaction time when I have to click on the mouse with my right hand versus the reaction time when I have to click on my left hand. I expected there to be no difference here, just for the record. I was actually surprised it came out as different as it did. I suspect if I repeated it, it might not look that big, but let's do our t-test on it because this is just the kind of situation that t-tests were invented on. Should I believe that there's a difference here or not? So we calculate it just like I said. Here's all our left hand values. Here's all our right hand values. Here's the means. Here's the ends. Here's the pooled standard deviation. We plug it into the formula and we get t equals 1.955. Now we do what I said, which is we calculate the t distribution. We see what is the probability of getting a t value this large or larger. In fact, we don't really need to do any of that. We just plug that number 1.955 into a piece of statistical software and we get a p-value out, right? It just does the calculate the area under the curve for us and we get p is equal to 0.791. The probability of getting a t-value of that size or larger if the null hypothesis is true, that is to say, if these 2 groups were sampled from the same population, the probability of getting a t-value of 1.955 or larger is 0.0791. So kind of unlikely, but not that unlikely. Okay, now let's do it by an ANOVA. All right, so here's our left hand, here's our right hand, here's our overall mean, here's our total sum of squares, here's our unexplained sum of squares. We plug these in. Again, we divide it by n minus 2. We get an F value of 3.8. It's different than our T value. But we do the same thing. We ask the software, what is the probability of getting an F value of this size or larger? And we get 0.0791. It's the exact same V value we got whether we did the t-test or the ANOVA. Actually, it turns out that if you got the t-value and we squared it, we would have gotten f. There's me just trying to prove it to you, right? T was 1.955. You square that, you get 3.82, right? ANOVAs and t-tests are basically the same thing. T-tests are just a special case of the ANOVA with some simplified maths. You can show it to be the case. You're just going to have to trust me. If you love playing with numbers, you can have a try and show it yourself. It's not that massively complicated to do. So ANOVAs and t-tests are the same things. T-tests are just a special case of ANOVAs where you've got two groups. How does regression fit into this?